So good afternoon to all of you. Today we are going to start a new topic known as feedback. Okay. So what exactly is feedback is? First we'll focus on negative feedback. Okay. What it is if you have an amplifier out here, okay, which has an gain, open loop gain of AOL. Okay. OL stands for open loop. Open loop means it defines the relation between x0. xi is the input, x0 is the output. Okay. So x0 is a into xi. Okay. Here a stands for open loop. Okay. It's written a out here. In the figure out here, it is written AOL. Okay. AOL is nothing but a out here. Okay. Now I am taking a portion of the output. I am sampling the output voltage and I am giving a feedback. Okay, a fraction of that. So beta is that defines the relation between x0 and xf. Okay, so beta into x0 is xf. That is, xf stands for x feedback, x0 stands for output. So a fraction of the output is again given back into an difference amplifier. Okay, so this takes a difference of these two signals. Okay, this is the input signal. So difference of these two is given to the into the amplifier. Okay. Now so this is the schematic. Now let's try and understand what is the advantage of doing this. Okay. So I can write. Now let me change the size of the mouse. Okay. Now the advantage is xi can be written as xs minus xf. Okay, this is the signals input signal minus the feedback signal. Okay. Now the feedback signal is obviously a fraction of the output signal which is given by beta. Okay. Now x output is again a times the x input to the amplifier, not the input which is coming from the source. Okay. Xi is the input to the amplifier. So a into xi. So x0 xi can be written as xs minus xf. That is the source signal minus the feedback signal, right? So that has been written as that, and then xf itself is actually beta times x0. So that has been substituted here. So now this portion I take it to the left hand side, and then I bring it to the denominator. So this becomes x0 a into xf or 1 plus alpha beta. Okay. So if I try to find out the loop gain now the loop closed loop gain, it is known as closed loop gain AF, whereas A is known as the open loop gain. Now by doing a feedback, now my new gain is given by A divided by 1 plus A beta. Okay. Now generally A beta is much greater than 1. Okay, A is gain, right? So gain will be high, generally of the order of 100 or 1000 like that, and beta. Okay, so this A into beta may be less than 1, but still since A beta is going to be a big value, so I can call it A beta is also called as loop gain. Okay, and that is generally less than 1. So the feedback gain can be approximated as 1 by beta. Okay. So obviously now the gain is reduced like drastically. Okay, the gain is reduced by giving a negative feedback. But the advantage out here is, okay, like initially when we talk about the gain of an amplifier, okay, so it is like GM into R0, right? For a normal common source amplifier or a differential amplifier, all these GM, R0, they are all coming from active devices and from they are all dependent on an temperature and a process variation and a voltage variation. So they are all not that very stable. Whereas this beta network can be from passive networks. You can just put two resistances and make a potential divider, right, and take. So this is more stable. So the gain is much more stable as compared to AOL for a wide range of input signals. So that is what we achieve by doing negative feedback. There are several advantages. We'll take one at a time. So right now we are telling the gain is reduced. Okay, now the gain is much lesser as compared to the open loop gain, but then since beta is generally A is generally, and it has got a dependence on the many application parameters and which will have lot of tolerances, whereas beta can be a mere passive components in which the tolerances can be tight, and hence it gives a much better stabilized gain. Okay, so we'll take one example, although we will again try deal with this in detail in the towards the end of the class, but I have just put two circuits out here just to give a feel of what feedback is. Here you have a common source amplifier. Okay, the gain will be GM into R0, correct? GM R0 is this is what we learned till now. GM R0 is the gain. Now I am giving a capacitor out here, two capacitors C1 and C2, and we are trying to find out what is the gain. Here one thing we are assuming that C1 and C2 is much higher than R0. Okay, that need not be the case. That subsequently we will do that analysis also. Right now we are assuming that R0 is pretty higher than C1 and C1 and C2. The impedance offered by C1 and C2 is much higher than R0. Okay, so the open loop, the gain from point X to point V out will be GM R0. Okay, it continues to be GM R0. Right now, if I see the current which is coming from V in, since there is no current which will flow into M1 transistor, right? Again, we are making one more assumption out here. That the gate capacitance is much lower than C1 and C2. So we are not neglecting the gate capacitance thing also out here. So the current which is flowing into the X node, okay, from here to here, okay, that has to flow through C2. Okay, so we are trying to equate those two currents. So the current will be V out minus Vx, okay, V out minus Vx into C2. So that current will come like this. That will be Vx minus Vn into C1 into S. Okay, now is this okay? Is these two equations okay with all of you? Is there any doubts? Anybody? Yeah, is it okay, Abhishek?
Sir, what formula you had used for this current?
Current is current is a voltage divided by impedance, and impedance is 1 by Cx. Okay, so that's why it comes into the numerator.
Okay.
Correct. It is for a resistance it is V divided by R. Capacitance impedance is 1 by Cj omega, right, or 1 by Cx. So that is why this has come into the numerator. So we write this, right. So now if I substitute the value of from these two equations, and I can remove the value of Vx, okay, and if I write just in terms of V out and V in, so this is the equation which I will get for gain. And if I consider 1 by Gm into R0 is much, this is a big number, and 1 by Gm will be a negligible number. So the gain can be approximated by C1 by C2. Okay. So we'll solve some of the problems of feedback, but here I just wanted to show, if we put a feedback like this, now the gain is just a function of C1 and C2, and we can fabricate C1 and C2 more precisely than fabricating M1. Okay, and the value of C1 and C2, okay, also is not going to change much with the biasing conditions, or with an VDD variation, or with temperature variation, unlike the parameters of M1. So you see the gain is more or less very stable. Yes, somebody had a question.
Sir, why C1 and C2 both current are same?
See, we are talking about a small signal equivalent circuit. So the current coming from V in, it cannot go here, right? Because we are assuming again this transistor has got CGS and has got very small as compared to C2. So this current which is coming here, okay, here there is a big impedance out here because this capacitance is small. So that current has to go towards the top only. That is the only way option available for the current to flow. That is why these two currents are same. Is it okay?
Okay.
Okay.
Sir, one doubt.
Yeah.
You mentioned here the capacitance of MOSFET is lower. That's why current will move to C2. So,
Yes.
like I didn't understand the relation of flowing of current with the capacitance value.
No, see, it is like it is a low resistance, it is a high resistance. So you can say, although this current can go in this branch and this branch, right? So this
So you are
capacitance
considering
this is a very high
impedance?
impedance. Yes.
Okay, 1 by C is coming.
Yes, 1 by C. So small capacitance means high impedance. So some negligible current is going here. Most of the current is going into the top. Is it okay now with all of you?
Okay, sir. Okay.
Okay.
And that's what the assumption is.
Yeah.
You are considering the value of R0
Yes.
very less compared to the value of C1 and C2.
And that is why this gain I am still writing as GMR0. Otherwise, the impedance seen here will be different, right? GM into, okay, this C also I have to consider for computing the gain. We'll do that subsequently. Time being, just I want to drive this point of gain desensitization. Telling that gain is more or less independent of the size. So, otherwise, for computing the gain also, this C2 also will come into play. Okay, but I am assuming right now, for simplicity, that R0 is much lower than C1 and C2. Okay.
Sir, so desensitization means because of feedback, our gain is not sensitive to other parameters.
Yes, correct, exactly. Because of feedback, the gain is not. You see, the value of C1 and C2. See, for VDD variation also actually GM will change because a small VDD variation will cause the operating point to shift, right? The current will change. So obviously, the GM will change, R0 will change, current will change. Similarly, process variation also. Okay, the capacitance, the tolerances will be much better in fabricating a capacitance than in a MOS transistor. Okay, so these are the reasons. Okay, now let's talk about other advantages of negative feedback. So feedback, forward gain feedback is given by A plus 1 plus. So we are I am differentiating it with respect to A. Okay, beta is constant. Okay, beta is constant because that is a pure resistive network or a capacitive network, which is not which doesn't vary. But A varies, okay. A is a thing which can vary with loss. So I am assuming A to be a variable out here, and I am doing the differentiation. So in the denominator I have one square, and then I have the same denominator out here. Differentiating on the numerator, I get a dA minus. Then I put this A and differentiating the denominator. So I get a beta into dA, right? From here, if I see here, so this dA, so plus A beta minus A beta, they get cancelled, and I have just dA here, and 1 plus A beta square. Okay, but A divided by 1 plus A beta is the forward gain. So I split this into 2, leave 1 here, and get the forward gain out here. So I get an A out here. Okay, so I put one A on the numerator and 1 in the denominator. So one denominator remains here. But that numerator A with 1 plus alpha beta becomes AF, which is brought here. Is this equation clear to all of you, or should I write it down further? Is it okay with all of you? Or let me just write it.
Yes. Good. Sir, it's clear.
It's clear. Okay. So now if you see here, what is this? Change of forward gain, relative change of forward gain. Okay, feedback. Okay, this is dA by A. Okay, dA. What is dA by A? See, this and this, right? Now this has got divided by 1 plus alpha beta. That means the forward gain is much more stable, right? It is much less sensitive than the without feedback. So without feedback, this is the thing. Okay, when I have to find out with feedback, I have 1 plus a beta in the denominator. That means this is much better by a factor of 1 plus a beta. Okay, so this is one advantage. Is this advantage clear to all of you? What is the advantage? Okay, okay. Here we saw the same thing out here, right? So this is again, this is just another way of explaining the same thing. Okay. Now we talk about bandwidth extension. So okay. In the bandwidth, see again at high frequencies will be written as AM divided by 1 plus S into WH. Like where this is the first, assuming there is one pole. Okay, the dominant pole, one dominant pole. Okay, we learnt about frequency response also, right? So this is the dominant pole. So this is the bandwidth WH. After this is going to fall. Now this is for the normal without feedback. Okay, this is AM stand for mid band gain, mid band gain, and this is, there is a pole. After this pole, it is going to fall. Now the feedback is given by AS divided by 1 plus beta AS. So I write AM divided, this whole thing is A, right? Okay, without feedback, 1 plus beta this thing I write. Okay, so I take this LCM and I modify this, so I get this equation. Now in this equation, on the top you see what is there, AM into 1 plus AM beta. That means the gain is reduced by a factor of 1 plus AM beta, right? Also the bandwidth WH has got multiplied by this. That means when I give an feedback, the gain will reduce by 1 plus A beta, right? AM by 1 plus beta. But same time the bandwidth will increase by the same factor. Is this okay with all of you? Yeah, Ashutosh, is it okay?
Yes, sir.
Okay, so this equation, so from this equation we can see that the amount, because of the feedback, negative feedback, okay, the gain has reduced by a factor 1 plus AM beta and the bandwidth has increased by the same amount. So that is one more advantage of an negative feedback. Now see this is the initial response. Suppose this is the initial response. Here you have some the coupling capacitors, like we discussed in the frequency response. There could be an issue with the coupling capacitor, so there could be low DC signals will not be passed, and again at high frequencies, okay, because of the CGS values, there could be, because of the capacitance of the MOS devices, again the frequency, there will be a pole here. Now when I am using a feedback, okay, the gain will come down. So this blue line which is shown here, that is with the feedback. So the gain will come down, and proportionately the bandwidth will increase. Okay, so without taking log, the gain bandwidth product will generally be the same. Okay, so gain and bandwidth, the product will be the same. Okay, now so that is why this gain has come down, the bandwidth has increased. Okay, so that is another advantage of negative feedback. Okay, so let's see, there are more advantages. Okay, now suppose I have an amplifier, right, which is 10 megahertz, okay, bandwidth, okay, and the gain, high gain 100. That is one option. I am sending a square pulse. I am, instead of a square pulse like that, I am using now my total requirement is on a gain of 100. Now instead of that, I am using a negative feedback amplifier with gain of 10. So if I use a negative gain amplifier of 10, okay, now my bandwidth from 10 will go up to 100 megahertz. Okay. Similarly, I am using 2 in series. So I will total, again I will get a gain of 100, right, instead of 1. So I am using 2 amplifiers. each with a negative feedback, and I'm reducing the gain to 10, and I'm increasing the bandwidth from 10 megahertz to 100 megahertz out here, right? So if I give an pulse like out here, so this is the response which I will get here, whereas in this the final output will be like this. Okay, so what could be the reasons? Can anybody guess?
It's allowing higher harmonics to pass through.
Yeah, exactly. Who was that? Gokhale, right? What is an square waveform? Right? What is a square waveform? Actually, you might have learned Fourier series, right? If this is 1 kilohertz square waveform, actually to get a square waveform, it will be 1 kilohertz square plus 2 kilohertz square plus 3 kilohertz and higher harmonics. They all together they make the square waveform. Okay, so you might want to refer to a Fourier series for that. Okay, so for 10 megahertz, and certain components will be passed, right? So you will get this kind of only few components of the square wave will be passed, whereas 100 megahertz more components. This is actually sum of so many frequencies together, so many sinusoidals. Okay, so because of this higher bandwidth, the output waveform will be much better. Is it okay with all of you?
Yes.
Okay. Okay. There is one more aspect to it. When I'm designing this amplifier, okay. So I am operating it at a particular operating point, but if I am going to give such a large input signal, okay, the operation point, the Q signal, actually when we saw like DC operating conditions, right? So now when you are giving such square input signals, the DC operating point also gets disturbed. Okay, so generally some transistor will come out of saturation and the gain will drop. So you will have non-linearity like this. Okay, for certain region it is linear, and then slowly the gain drops. Okay, so that will also cause distortion in the output waveform, right? Whereas here the gain is only 10. So you can this can handle from 0 to VDD by 2. This can handle from VDD by 2 to VD. So accordingly you can select the biasing point of these transistors and a certain more linear region of operation. Okay, so that is the second reason why we get a better waveform from having these two cascaded stages with negative feedback rather than a single amplifier. Is the two reasons clear to all of you? Is this non-linearity, why does this non-linearity set in? Is it understood? Because all amplifiers, we generally have that input common mode range, right? So when you try to make one amplifier trying to cater for the entire thing, then obviously it will come out of the saturation region. So you can't. So when you split it into small operating regions, then accordingly you can do the sizing of the transistors and make it a linear kind of thing, right? Is it okay with all of you? Okay. So
Sir,
yeah,
can you explain this aspect again?
This thing.
Yeah, linearity, and sir, here this is a negative feedback in B figure, or because here there is no negative feedback is shown here.
Here? No, it is a negative feedback amplifier, okay?
Okay.
It is a feedback amplifier, negative feedback amplifier.
And the first one is not negative feedback.
It is just a single amplifier.
Okay.
These are two negative feedback amplifiers, and that is the reason why this gain has been reduced to 10, okay? And the bandwidth has increased. So the gain bandwidth product is same here if you see. Okay?
Sir, can you explain this linearity aspect again?
Okay. See, when you design an amplifier, okay, suppose you are making a digital signal, okay, you have made a comparator, okay, and you are making giving a signal out here, right? This is like, actually this changes the small signals is okay, it doesn't change your operating point, but if you are giving such signals, it will change your operating point, right? DC operating point also of the amplifier. So there is a possibility that transistors will come out of saturation in those cases. So it is very difficult to design an amplifier for a large input common mode range. So obviously the gain, since it's changing the operating point itself, the gain cannot be constant. Gain is what? GM into R, right? Right? And GM and
Yes.
R are both proportional to the currents. And when you are changing the input by a large amount, the currents will change. So GMR will change. And hence this will not be a straight line.
Correct.
But now I am splitting that range into two. Okay, I am getting only half here, half here. So the input range from here, which this amplifier has to tackle and this amplifier has to tackle, will be lesser.
Sir, input range will be the same signal, correct?
No. Say this has to cater for 0 to 0.2. Okay, this has to cater for 0.2 to 0.4.
Okay.
Right? But the range is just 0.2 range it has to cater. This also, whereas here 0.4 range it has to cater. So this will be, the linearity will be better in these.
Okay, so we are getting gain in two stages, so that's
Yes.
why it is
Yes.
splitted.
Yes.
Okay.
Right?
Okay.
Right? These two transistors, this will be optimized for this particular input range. This will be optimized for into the gain. After the gain, what we are getting, this can be optimized for that. They're not
Okay.
exactly the same. Okay.
So,
Yeah. Yeah. Tell me.
but for second case also, the VN will be the same for the first amplifier, right?
Yeah. Vn will be the same. Vn will be the same.
So that has to cater for that same as how the previous one was doing. I'm not able to
Yeah, Vn will be the same, right? But since it will be only since the range is only this much. Like if the gain is not that much, it will be linear. If the gain is high, it will go and make this kind of a curve. Is it okay?
Okay.
Right?
It has to cater lower gain. So it is not dealing
No,
with
I
the
understand your
region.
point. Okay. Now, this is a Vn. In the first case, in the second case, both it has to cater for this input range. Okay. Now, for this amplifier, as long as the output is this much, it is kind of linear. Okay. So, in the first case, I am restricting my gain till here. So, the signal will be like this. It will be linear. Right? The gain is only this much.
Okay.
So V out only will be this much. So this will be linear. This portion is linear. So this will be linear. Gain is less. Okay. So this particular rolling off will not be seen here. That rolling off will happen if the gain is high at this V out. Is it okay? Kumar?
Okay. Yes, sir. Got it.
Yeah.
Yes, sir. Got it.
So okay. Now another our last class will be on noise, but let me just touch upon this aspect also, that there is the feedback. Yeah, tell me.
Sir, previous slide.
Yes.
Sir, can the linearity be explained in terms of Bode plots? Because we are increasing 2 poles in the second case. So the linearity will increase. In the first there will be no pole, but in the second case we are increasing 2 poles.
No, actually we can't really talk about linearity in terms of Bode plots. Okay, because we are decreasing the gain. That is going to help in the rise time and the fall time Bode plots from here. Okay, bandwidth. This is linearity doesn't come from Bode plots. Okay, this is actually DC operating point itself. It has got an input range is this much, but since the gain is less, okay, this linearity issue will come when you have set a very high gain. So that we are avoiding in this particular circuit. Okay. So noise reduction. So suppose this is an amplifier. Okay, there is an input. We are just talking about the noise. There is some input noise which is coming here, right? And without feedback. First, without feedback. So this network is not there. Without feedback. So this noise will get amplified by the gain, right? Now this amplifier doesn't know whether it is a noise or signal. So it will amplify the signal and it will amplify the noise also. And also this amplifier itself will create some noise, okay? Because there are resistances, transistors and all. So each one of them will create some noise, okay? So that noise also. So this is, I have given that as noise amplifier. So the output out here will be, output noise will be the input noise which is getting amplified as well as the noise which is created by the amplifier. Okay, so this is known as output referred noise. Okay, so this is output noise available out here. Now with feedback what happens? Okay, now noise with feedback, this signal, what is this xi, right? Xi is getting amplified. Okay, what is xi? Noise in minus beta noise, because this feedback is given here, minus beta noise out, okay, plus noise amplifier. This noise amplifier, that is going to remain constant, right? In this case also it will be there. With feedback also this noise from the amplifier will be seen here. So that I am writing here. Okay. Now since this is the total noise is n out f, okay, a fraction of that is given as feedback. Now that's why I have taken beta into n f out, okay, here. So and the difference of that is being amplified by this amplifier. So that is. Now if I rearrange these terms, I will get here. And now what you see here? Now if you see here, the noise, okay, which is coming from inside, okay, that is getting attenuated. Initially it was a n I n. It is now 1 plus a beta. So the input noise is getting attenuated 1 by a beta. So this is not a great achievement, because the signal is also getting attenuated by the same factor. So I can't say this is a great advantage, but what is of advantage is this. Okay. Now initially it was a n amp. Now it is getting attenuated. So the noise generated by the amplifier internal components with feedback, okay, it is getting now divided by a factor 1 plus alpha beta. Okay. Now if I talk just in layman's language, some amplifier, it is generating some noise out here. You are taking a feedback from here and giving it here. Okay. So you are doing an inverting that signal and giving here. So they will get cancelled. If I write beta is equal to 1, right? So then this whole noise can get cancelled. In fact, if I put a into beta is equal to 1, then the whole noise can be cancelled. But it will become a unity gain amplifier. Even the signal also will have the same gain. Otherwise, it is like noise is getting divided by a factor 1 by a beta. Is it okay till here? What are the advantages of negative feedback to all of you?
So, sir, this is a adder. This input and output of this beta, it is going to add here. This circle is showing adding.
No, subtracting. Plus and this is minus.
Sir, that's that minus is because of the negative feedback. But here at the end, this operation.
No, not necessarily. Here I am not talking about negative. Here I am not putting any negative. So this could be a positive of xi and x0. It is a generalized form. If I am getting a negative xo out here, okay, then I can put an adder out here. The negative feedback just means that they have to be out of phase.
Okay, or either we have to subtract.
Yeah. If it is of the same phase. For example, if you are talking about CD amplifier, like source follower, where the input and output are following each other, right? They will be in phase. So in those cases, you will have to have a mechanism where they are not added. Okay. So this is a generalized. Okay. Now there are different kind of amplifiers. Now one is known as an voltage amplifier. Where you give an input voltage, you get an output voltage, amplified version. There is something known as transimpedance amplifier. You give an input current and you get an output voltage, right? So here the gain will be known as G or AV. Okay. Here it will be called as trans impedance, so it can be called as R, right? Because V out divided by V in is equal to R, right? So that means I in into R is equal to V out. So this generally the gain, what we have been calling as G here. This will be A into V. This generally will notate it, will give a notation AV. This will give a notation R. Okay. Is it clear why we call it as R, transimpedance? Because it is the current, input is current, output is voltage. Okay. Similarly, I can have a transconductance where input is voltage and output is current. Here it will be GM. Okay. And similarly, I can have a current input and current output. So this will be known as a current amplifier. Okay. So now if you see here, the physical implementation is given here. I have an V in. This is a simple amplifier, V in and V out. Okay. So I have an gain G, which will be given by GM into RD. Okay, which is unitless actually. Okay, because it is it. Or I can pump in a current here into this configuration, and that current will flow like this, right? And output voltage you get. So now here this becomes an transimpedance, right? Here the gain can be called as R. Okay. Similarly, this is just input voltage and output current. Okay, simple transistor. So this will be called as transconductance amplifier. And you give a current here, you will get a similar current here and a fixed bias here. The AC signal, if you consider. So this will be a current amplifier. Okay. So a better implementation of these circuits is shown out here. V in, RD, and then you have an CD amplifier here. Now here obviously it is V out and V in is totally isolated, but you will find that okay, this is a voltage amplifier clearly, right? Similarly, this is a transconductance transimpedance amplifier where you give a current here. So accordingly a voltage will be developed here. Based on that voltage, again a voltage will be developed here. So this is current in and voltage out. This is voltage in. So here also you will have a voltage. Based on voltage, some current will flow in this particular circuit. So this is the input circuit. This is the output circuit. So between the input in the input circuit you have V in the output circuit I have I out. Similarly, here I have an input current coming here, a fixed bias out here. So this is an RD. So this will generate an voltage out here. That voltage is given here. So I have I out. So these are the four kind of amplifiers which we can implement. Is this okay with all of you till here?
Sir, one doubt.
Yeah.
So sir, if we say transistor, so it means a transfer of resistance, like input resistance is high and output resistance is low. So we are transferring resistance value. Yes. So in here, transimpedance means we are changing impedance here?
No.
Like input to output?
No. Transimpedance means trans means transfer. Impedance means the ratio between V out by V in is an impedance or a resistance. Impedance is a general term for resistance, right? V out by I in. Okay, what here how do we specify the gain? We say voltage gain, V out by V in, right? Here we will say V out by I in. Okay, and what is voltage divided by current? It is resistance, right? So that's why we call this as transimpedance. Here is I out by V in. Okay, the gain of this amplifier. It is I out by V in. So I out by V in is what? Conductance, right? So we call it as transconductance. Here is I out by I, so it is current amplifier. Is it okay?
Sir, okay.
Huh.
But like in transistor, we say that transfer of resistance, like from high resistance to low resistance, we are moving. But here, how can we say, is there any relation for trans impedance? Means impedance of input and output is changing?
No. That's what I'm telling. This has come. This is an alternate name for gain of this amplifier.
Okay.
Okay. What is gain of this amplifier? Voltage input is the current and output is voltage, right?
Okay.
So I have to define a relation between output and input.
Mhm. Okay,
So V
that's
out
right.
divided by V in, right? So that is resistance. So the name comes from there.
Okay.
Resistance or impedance,
Mhm.
right?
Okay.
Is it okay?
Yeah.
Okay.
Sir, a direct connected load in a mirror circuit is an example of trans-impedance amplifier because you're applying the current and getting a voltage in between. And that voltage again reflected in the form of current.
Pardon, I didn't get you.
Diode connected loads in current mirror circuit.
Diode connected load. Okay.
In a current mirror circuit, in which we have a current source which is getting mirrored, and in between we're getting a voltage.
Yes.
So the diode connected.
Yes.
That is an example of trans-impedance.
Correct. You can call that way. Okay. So now there are various kinds of topologies. Okay. Excuse me. So the first kind of topology. Now these names can be slightly confusing because various textbooks use a different type of nomenclature. Okay, so just be careful with how the nomenclature are used here. Okay, this means this is an suppose this is a voltage amplifier where voltage is given as an input and voltage is given as an output. In that case, we sample the output voltage and give it as in series to the input voltage. Okay. Okay. Obviously, these have to oppose each other. The phase has, if already there is a phase 180-degree phase difference, then you can simply add it. Or if there is no phase difference, then you will have to do an subtraction out here. Okay. So this is actually a difference. Okay, so difference between these two signals. So for a generalized this thing, we will assume that V0 we are giving it here and we are subtracting these two signals. So this will be known as voltage series feedback. So this is an mix and match. Here we are calling it as sampling is the sampling of the output. We are calling as voltage or current. And the connection which is given here, we are calling it either series or shunt. So when we are using this mix match terminology, okay, because we'll see here, we can call it as a voltage amplifier like this. Okay, so here it is not mix match, or you can call series shunt series. Here also it is not mix and match. Okay, here it is a mix and match, voltage and series. So whenever there is such an mix and match, okay, then the first term indicates what is being done to the output, and the second term indicates what is being done at the input side. This is output side, this is the input side. Whenever there is a mix and match, voltage series, that means a voltage is sampled and connected in series out here. Okay, so this is applicable to voltage amplifiers. Okay, then you have something known as voltage shunt. Okay, so in this case, input is current and output is voltage. In that case, you are sampling the voltage, and whenever a current input is being given, you give a shunt feedback. So this is known as voltage shunt feedback. Similarly, if you are sampling the current which is flowing into the load resistor, and based on that current you are giving you are making an voltage out of it. Okay, proportional voltage, and giving it in series here to the voltage. Okay, this will be known as current series. Okay, because you are sampling the current, converting it into voltage and giving it in series. So whenever there is a voltage source here, you have to give it in series feedback. Okay. So it is like current is being sampled and it is giving in series out here. Then you could have a current shunt feedback where this output current is being sampled and that current is being given as a feedback. Here it is current input and current output. So this is known as a current shunt feedback. Okay, so this is another topology. So these are the 4 kind of topologies. When we see the actual circuits, it will be more clear. Timing, just understand there are 4 kind of. Okay, so you can sample the output voltage or sample the output current. Okay, both options are available with us. In the top 2 cases, the voltages is being sampled. In the bottom 2 cases, the current is being sampled. Okay, and now after sampling, you can either give it in a series with the voltage source. Okay, so that becomes a voltage. Okay, or you can that becomes series. Okay, series, because it is being given in series. Or you can given current, whenever you want to give a current feedback out here, it will be in parallel. So in that case, it will be a shunt feedback. Okay, so these are the 4 different kinds of feedback topologies.
So
yes.
when input we are giving in the form of current, then we have to connect in the shunt.
Yes. Yes.
Okay.
Okay. Whenever input is in current, you have to connect in shunt. Whenever it is voltage, you have to connect in series. Okay. So that is that. And whenever the output is in voltage, okay, you will take a voltage feedback, and whenever the output is in current, then I take the current feedback. Okay. So this is from some other textbook in which the same thing is the name here is different. Voltage amplifier, it is known as a series shunt. So series shunt means here this series refers to the input side, this shunt refers to the output side. Okay. So voltage is being sampled out here, so this becomes an shunt because parallelly you are taking the voltage, right? Voltage is always, measurement of voltage is parallelly, so voltage is parallel. So this is the shunt, this is on the next side. Okay, so this is the input and this is the output. Here you are giving, so this becomes series shunt out here. Okay, so this is different textbooks use different kind of because for why I am covering these 3 from different textbooks out here is because you will find various numericals in various textbooks. Okay, so that is the reason I am giving some how the nomenclatures are being used, so that you can refer to any textbook for numericals for practice. Okay, so that is the reason. Otherwise, I could have stuck to our textbook and followed that. I am giving a hint of what other textbooks are there, so you will find a lot of numericals in other textbooks also. Okay, here if you see here, it is shunt series. Okay, shunt series means this is shunt, and the input side it is shunt, in the output side it is series. Okay, here it is for transconductance amplifiers, it is series. That is, current is being sampled, and again here also you have series. So obviously this feedback network has to convert this current which is being sensed into voltage. Okay, here it is the voltage which is being sensed, and feedback is also voltage. Here it is current is being sensed and current is being given as a feedback. Here again voltage is being sensed, but current is being given here. So this voltage, this feedback network has to give an feedback current which is proportional to the output voltage out here. So these feedback networks will be different for each of these topologies. Okay. So now let's first take the case of series shunt or voltage feedback circuit. Okay, so this is an amplifier where this voltage will be amplified by a factor of A. Okay, so V feedback. Okay, this network is a feedback network where it samples the output voltage, and beta times V0. Okay, will be given out here, right? So Vi is this voltage minus this voltage. So Vs is equal to, so Vi. Okay, Vi is Vs minus and V out. Okay, V out here will be A times that. Okay, so we are neglecting the current which is going to flow here. Open circuit analysis we are doing. So it will become beta V0. So now this is the forward gain, right? And V0 divided by, so this is what we did earlier. Okay, so the same derivation. So I get a forward gain of A divided by 1 plus beta A. Okay, this is what we learned earlier. Now let's talk about the input resistance. What happens? Okay, so RIF, input as seen into the circuit, will be Vs divided by II. Okay, the circuit which is flowing in this current. So Vs divided by what is II? Vi divided by Ri. Ri was the initial resistance before feedback. Now after feedback, what it has become, that we need to find out. Okay, so Vi is this voltage across Ri. So Vi by Ri, right? So I am writing Vs by Vi, right? And Vs by we found out that equation, right? So I write in a Vi beta Vi by Vi. So I get Ri is equal to 1 plus A beta, right? So what we are seeing is, whenever we are giving in negative feedback in series out here like this, right, the resistance increases by a factor of 1 plus alpha beta. So you don't even have to remember these derivations. It is straight away. You need to try and find out what will be the beta, what will be the open bit. And if it is in series, it is well understood, right? If you are adding something in series, the resistance will increase. By what factor? 1 plus A beta. Is it okay with all of you?
Yes, sir.
Yeah? Okay. Now, if I try to find out the output impedance, what has happened? Okay, because of the feedback network, right? So I am going to apply an output voltage out here. Obviously, I'll put this as 0 in that particular case. Okay, if I put that 0, if I am applying an output voltage out here, okay, beta times output voltage will be available here. That will be available across Ri, and this voltage. So now V0 will be, I am applying a voltage here. The current will be I0. So this voltage V0, which I am going to let me, yeah, it's here. This voltage which I am applying. So R0 of, this was the initially which was available, that is there, plus one voltage source. And what is this voltage source? This will be, because now this Vs is not there, right? So this whatever voltage I have applied here, beta times of this voltage will come here, and it will get multiplied by the gain. So AF Vs, this will be available here, right? So V0 will be I0 R0 minus beta A V0, right? So from here V0 by I0 I write. So with feedback, the output resistance will be, initially it was R0, now it gets divided by a factor 1 plus beta A. Okay, that means, now again it's very simple to remember. If I am taking some parallel connection, when I see from here, the resistance will obviously decrease, right? Right? So when I am sampling a voltage, when I see from here, the resistance will decrease. So by it is always gain, everything will happen by a factor of 1 plus beta A, right? So the gain will, so for a voltage series, there are three things which will happen. Okay, bandwidth, gain, okay, input resistance and output resistance. Okay, so gain will reduce by 1 plus beta A, and bandwidth will increase by a factor 1 plus beta A. Input resistance in this particular case will increase by a factor of 1 plus A beta, and the output will reduce by a factor of 1 plus beta A. Is it okay with all of you?
Sir, Vi should be beta V0 plus Vs, no?
Vi should be
voltage across Ri, sir, would be equal to Vs plus beta V0. Vs plus beta V0.
No, minus, because it's a negative feedback. If you see the polarity. Okay.
Okay. Then in that case, sir, AVI has replaced by A into Vs minus beta V0. We have only written beta V0 in V0 in that equation.
In this equation,
the V0 is equal to I naught minus beta A V0. We have only replaced Vi by beta V0, but Vs has to also be included in that factor.
No, see,
in V0 is called I naught.
V0 is V out is A into Vi. Vi is this voltage, right?
So that voltage is
that
equal
is Vs minus Vf, and Vf is beta V0. Is it okay? Right? This voltage is Vs minus Vf. That is what we have written here, right? Vf is beta times V0. That is we are substituting that, right? And this voltage is A times. So the gain, open loop gain of this particular box is A. So I'm multiplying it with A.
Understood.
Sir.
Yes.
Yeah, tell me.
So the circuit which is drawn below, that is the equivalent circuit for this upper circuit, right?
No. This is a circuit which has been, the bottom circuit is a circuit which is drawn to compute the output resistance, in which I am giving an output voltage. If I give an output voltage out here and I am giving Vs is equal to 0, then this is how the circuit will look like.
Okay, then Vs will be 0 here. We are just representing Vs.
No, sorry, this is then this is an equivalent circuit where Ri has been replaced by Rif and A has been replaced by AF, and ROF, this is equivalent of this. Okay, RO has been replaced by ROF. Correct. Okay.
Sir, one doubt.
Yeah.
You told by just looking at the output, it is visible like output impedance should be decreased. Like I didn't understand that looking at the circuit.
See,
can you explain that?
If you are taking a parallel connection, okay, for your feedback network, right?
Yeah. Okay.
That means anything if you are taking, when I am applying a voltage here, if there is a parallel path, it will decrease the voltage, decrease the impedance, right? When we see some actual circuits, it will be clear. Okay.
Okay.
When we are looking from here, if you have a parallel path, obviously the resistance will decrease. Okay. I am going to solve some numericals. It will be clear by then.
Okay.
Now I can have an second amplifier, which is current to voltage. So here I'm pumping in some current out here, right? So now here I0 out. No, I'm giving a voltage and I am taking a current into the load here. The load will be connected between O and O dash, right? So without feedback, I am calling it as GM. Okay. So GM. Okay. What this is going to convert? So I0 is equal to GM into VI. This voltage VI, right? And I am giving I am taking that current, converting it into voltage and giving it in series out here, right? So now this becomes Vs plus beta I0 here, because what is this feedback network doing? It is sampling the current and converting it into current. So I am writing beta into I0 here, right? Now I0 by Vs, okay, with feedback will come as GM was the initial one. Now it will come as 1 plus beta GM. Is this okay with all of you? Okay. So here what is the unit of GM? It is ampere by volts, right? Because this is current and this is voltage, right? So GM will be ampere by voltage. And what is the unit of beta? It is converting current into voltage, right? So beta will be in resistance, okay, ohm. So these two, when they when they multiply, okay, so this will become an unitless thing. Then again, still you will get it as a GM only, because I0 by Vs has to be GM. So that is how the units also match. Okay, is this a derivation clear to all of you? Right? Okay, so after the class, just write these equations yourself. So it is pretty simple, right? Okay, only thing is instead of A, because here we are talking about a current, voltage which is being given here and current which is being taken out. So we are using the terminology instead of A, we are using GM with it units as A by V. Similarly, beta here, it is converting a current into voltage. Okay. So and hence this has become resistance. Okay, so that is the only difference. Again here, if you try to find out the input impedance out here, this is now Vs. Okay, initially it was Ri. Now if I write Vs is equal to Is into Ri plus this voltage, which is beta into I0, right? And I0, if I substitute from this equation, I can write it like this. Again, I take the Vs onto the other side and divide it by, I will get a new input resistance, okay, with feedback, which will be 1 plus beta gm Ri, because I am putting something in series out here. So it will increase the resistance by 1 plus gm. Here if I talk about the output resistance also, since it is, I am sampling a current, now I am making that output current to flow through my feedback network also, right? So it is a series connection here in the output, and if I apply a test voltage out here, okay, if I apply a test voltage out here, so the I test will be one current which is flowing in here and one current. So if I write those two equations, okay, and if I put Vs is equal to 0, then I get this equation. So I will find ROF is V test by I test. I will get it as R0 divided by beta GM. That means my output resistance, okay, here I think I made a mistake out here. R0 with feedback. So, yeah, it will be in the numerator, I guess, right? I made a mistake there. Here it is in see, I will go there, R0 V test. So I test is equal to V0 divided. Okay, I'll do the amendment in this slide and again, and before I upload it. Okay. So when I'm taking it in series, okay, ROF will be, this will be in the numerator portion. Okay. So I'll do that amendment and post it accordingly. Okay. Now if I have a voltage out here being given as a series to the input side, okay, that is another option which we can do. So here I am taking the voltage. So since I am taking this as a parallel connection out here, in this case again the resistance will decrease, whereas here I am giving it as a parallel connection, and hence the resistance in this case, okay, again here the resistance here also will decrease because this is again in parallel. So this is in parallel, this is in parallel. Both RIF and ROF will be lesser in this case because here it is parallel, here it is parallel. New connections which are there in parallel. Okay. Otherwise again for the gain, if you see here V0 divided by R, initially it was Rm, now it will become Rm divided by 1 plus beta Rm. Okay. Now I am calling the gain as R in this particular case. Okay. Because it is input is current, output is voltage. Okay. So A will be what? V by I. Okay. So that instead of calling it as A, I am calling it as R in this particular case. Is it okay with all of you?
Yes, sir.
Okay. So this is one, and the last one is current to current. Okay. So in this case, obviously, can somebody tell what would happen to the what will happen to the output impedance?
Increases.
Output impedance increases.
Okay.
And input will be decreased.
Input will be decreased. Yes.
Yes.
So
Into parallel.
yes. Okay. Input will decrease and output. Now, how to do analysis of these circuits? Okay. Initially, when we took this particular circuit, okay, we assumed that this voltage is GMR0. Okay, but it may not be GMR0 because I have put one capacitor here that will affect the gain also, right? So now we will do a more involved derivation. Okay, so first step is to identify what kind of topology it is. Is it a voltage amplifier? Is it an yeah. First, it is a voltage amplifier or a current amplifier. You have to see the circuit and identify. Okay, and if it is if you are sampling the output voltage, okay, so we make this circuit. Okay, we will redraw the circuit without feedback. Okay, now we will not completely remove the feedback. Okay, to understand the loading effects also. So what we are going to do is, without feedback, but those feedback elements we are going to incorporate in the circuit as a without feedback element. Okay, so what we do is, like if we are doing a voltage sampling, I will set voltage to be 0 from the output side, and then we take those components and put in the input side also. If I am doing a current sampling, I will put I equal to 0. Okay, and put that component in the input circuit. Okay, in the output circuit, similarly, if I am doing a shunt connection, then I will put Vi is equal to 0 and put that element in the output circuit, and I will put I is equal to 0. Okay, for a series, again I will put that element in the output circuit. Now this circuit, after redrawing with these conditions, this will become a normal circuit where you will compute the gain, okay, which will be open loop gain with loading. Okay, and then you understand what is what we are trying to do is, we are trying to compute the gain with loading. Okay, without feedback, but with loading of the feedback components, and then you find out beta, and once A and beta is found, then rest of the things you can use that formula and do. So we'll take some examples, then it will become clear. So let me.
Sir, what is the meaning of loading? You are saying that loading what?
Okay, loading is this sentence top this derivation when we did for this particular circuit. Okay, GMR01. Okay, here we made an assumption that R0 is much lesser than C2. Correct?
Yes.
Without this capacitance, okay, without this capacitance, I am calling the gain will be GMR0, right? So I am putting this capacitance. This is giving a feedback here. This is giving a feedback signal here. Also, it is going to load the output gain also. If CM is not much higher than R0, it is going to load the circuit also.
Load the circuit means load the gain means.
Load the gain means this is going to contribute towards output impedance. It is going to come in the output circuit also.
Okay.
It is just not a feedback. It is going to modify the terminal impedance at this place also.
Mm-hmm.
Okay, so that we are going to calculate. Okay, so that is the reason. Okay, I know all of these things are till now it has been very confusing to all of you, but that is why I have included few numericals. It will be clear. Yeah, tell
one
me.
more thing. The last slide that you explained, 2 slides back. Here, what is the meaning of shunt comparison? Like to find the output circuit, set Vi equals to 0 for shunt comparison. Comparison here means?
Comparison means giving the feedback in the input.
Okay, how we are giving feedback?
Yeah. Okay. Now, after 2-3 examples, things will become very clear. Okay, this is the circuit. Okay, can I call this as a feedback circuit? Is this a feedback circuit?
No.
Actually,
Yes,
yes.
sir.
Yes, it is.
Yes, sir. Yes, sir.
Yes, I am taking output from
Okay,
here.
okay,
Actually,
output.
that output is opposing this input, right? Is the output opposing the input?
Yes.
Correct?
Yes.
So this is actually a feedback circuit. Okay. Okay. So now, how to analyze this circuit? Okay. First one is, we will redraw this circuit without feedback, and for without feedback, okay, for the input side, okay, for the input side, are we sampling the output voltage or output current in this case?
Output voltage.
Voltage, correct?
Voltage.
Okay. So I short the output voltage to remove the feedback. Okay. So if I short that, in the input side, this will become like this, because I am shorting this. So this will become like this now. Correct?
Yes.
Correct? Yeah. See, just understand. I am going to explain 4 or 5 examples. If you understand these examples, all your problems will be easy. Okay. So try to understand each step. Okay. If you have a doubt, please let me know. Okay. Now from the output side, now input we have drawn. For the output, okay, since it is a voltage in series, I have to make it an open circuit. Okay. So if I make this open circuit, in the output circuit, will R remain or it will go? If I just open this circuit, will R remain?
R will remain, sir.
It will remain, right? So this R is shown here from source drawn here, right? So this is the circuit, okay, which is now from here the feedback has been removed, but the feedback element is still there. So we are going to, that is the loading effect we are still taking into consideration. Only the feedback has been removed. So from here to here, how is it done? Is it okay?
Sir, this R
Sir,
thing, can you explain?
Could you identify the
Yeah, tell me. See,
Hello.
see for the okay, let me start with one. Like for the input side, since we are sampling a voltage and giving here, we will short the output. Short the output means we'll short this, so R is removed here from the input side. When for the output side, I am going to open. If it is a voltage source, I will open it. Okay. So if I open it, okay, no current is flowing, right, in this particular branch. But from the output side, this R will be there, still be there. So that R is put here. Is it okay?
Yeah, so could you identify the input and output side?
This is the input loop and this is the output loop. This is in this circuit. This is the input.
Yes, sir, but we are taking output
From here.
from this, like source
From this.
source to ground.
Yes, source to ground. So that is why
But
here
we
it
are
is written
connecting
positive.
Drain became, sir, ground.
And why we
This
are connecting to
is no
drain?
more ground. This is no more ground here in this particular circuit.
Okay.
This is no more ground. From output is from this node to this node, right? From source to resistance, and this is the circuit.
The resistance became parallel to that transistor.
Yeah,
That is confusing a little bit.
because this is virtual ground, right? Again, for
Due
AC
to that,
analysis,
sir. Yes, sir. Yes,
for
yes,
AC analysis, this will be ground, right?
correct, sir.
So that is why.
Okay.
Due to that, it became parallel.
Yeah.
Yes.
Sir, this is like source follower, and so why we are calling it as it's a feedback, because gate source voltage is changing because of VO, right?
Correct. Correct. Okay. Now, so I can find out the open loop gain of this circuit. It will be V0 divided by Vi, right? GM into like R parallel to RD of this. Here, this is from Millman-Hall case. Instead of R0, they use RD. Okay. So it is RD into R divided by RD plus R. Okay. This is parallel to R0 into R. Is it okay? Okay. And then they use one more mu, they call mu as GM into RD. Okay, because this is the intrinsic gain of an transistor. So they use this mu also. So the gain of this particular is mu R divided by RD plus R. Okay, we have been calling R as R0. Is it okay with all of you? Gain is GM-RD, right? RD parallel to R0. That is what is written here. Parallel is RD into R divided by RD plus R. Is it okay with all of you?
Yeah.
Okay. So now this is the gain equation, open circuit. And tell me what is beta in this case? Beta is what fraction of the output voltage is fed into the input voltage, right? In this, the entire input voltage is fed as in the input circuit total. Beta is 1. Correct?
Yes.
Beta is 1, right? Now I know beta is 1 here. So I compute a D loop gain 1 plus A beta. So I get this, right? Now forward gain will be AV divided by beta. So AV is this divided by D. I get the right new AF, right? Now input impedance here is infinity because this is into the base of a transistor. So output is also infinity. Output impedance, if I see from here, from outside, it is R and R0 parallel, right? R and R0 parallel. Now will the output impedance increase or decrease in this particular case? It is a voltage sampling, right? Voltage sampling means increase. Okay, voltage. So I need to multiply. No, a voltage sampling means decrease, right? We learn
yes,
decrease. So I put it into the bottom. Okay. What is R0? R0 is parallel of these RD and RF, and I divide it by D. So I get this. So is it okay how to tackle these kind of circuits?
So what is D?
D is 1 plus beta A.
No, like what D represent? Like any terminology?
D?
Yeah, D.
D is known as feedback factor. Beta is known as beta AV is known as D. I am not very sure. Beta AV is known as the feedback gain. Okay.
Sir, what is the feedback element here?
Pardon?
What is the feedback element here?
Feedback element is this resistance.
Sir, here R0 dash is the output resistance of this amplifier.
Yes,
this is nothing but RB parallel R.
Correct. Correct. That gets, because it is a voltage sampling, that gets divided by the D. Okay, so you have to compute D. You have to compute AV. You have to compute an beta. Then you have to compute D. Okay, and then the equations follow. Is it okay? Yeah, Vishwanath.
Sir, again, your resistance and your input is connected to the ground. How your output signal is going to the gate?
Here?
Yeah.
See, this volt. From this output signal, along with the input signal, okay, the input signal minus the output signal is available to the gate to the source. That means Vs minus Vo. Okay, that is the feedback. Correct? To the input of the transistor, gate to source voltage. Is it okay? The gate to source voltage will be Vs minus Vo, right?
Yes.
Here beta is 1. So,
okay, your gate voltage is nothing but you're taking Vg minus Vs or Vout, the value that you considering as a feedback, is it?
Yes.
Okay, if that is the case, all the transistors will have a feedback, right?
No, depends on. If you don't put a resistance here, they'll not.
Okay, if you don't put, okay, if you consider if you take the drain side,
then there's no feedback there. If there is no resistance here, if there is a resistance on top, then there is no feedback. right?
Okay.
Here we saw
Degeneration.
Because of VGS minus VG minus VS concept, we considering we are taking output at source. That's the reason it is a feedback.
Yes,
right?
yes. Like
Okay.
where was that circuit? Here. Here there is no feedback. Here there is a feedback.
Yes, because your input is not depending on the drain. It is depending on source. Okay.
Correct. Okay.
Thank you.
Okay. Okay. Now, I think once we consider one more example, things will be clear. Yeah, tell me.
Sir, how beta is 1? I don't get it.
Because the entire voltage is available, VO is available in the input network. Okay. We'll see one more example where the entire voltage will not be available there.
Okay.
Okay.
Sure.
This entire voltage is available here. Okay. We'll see a few more circuits, then you'll be able to realize. Okay. Now see here. Okay. Now tell me, are we sampling voltage or are we sampling current? Forget about this circuit. Let's concentrate here.
Voltage.
Right? We are sampling voltage.
Voltage.
All are all are in agreement. Okay.
Voltage,
What is beta?
Depends on R1, R2.
R1 over R1.
Give me the formula for beta.
R1 plus R2.
Fraction of R1.
VO into R1 divided by R1 plus R2.
Okay. One at a time. What is beta? Beta equal to, tell me.
R1.
R1 divided by R1 plus R2.
What divided by?
R1 divided by
Beta,
R1 plus
beta.
R2.
R1 divided by R1 plus R2. Beta is that. Correct?
Yes.
Okay. Okay. Now tell me, you will be able to solve it yourself. Tell me. For in the output circuit, if I have to redraw this circuit, okay, since it's a voltage sample, I will put a V0 as a short circuit. Then what happens to the input side? R1 will be there. R1 will be there or not? I am going to short circuit this.
No.
I am putting a ground here, right? Will R1 will be there?
Both in ground.
It will
No,
be
no.
there, sir.
R1 will be there. What about R2?
R2 will.
It will become parallel to
R1.
R1 parallel to R2.
R1.
R1 parallel to R1. Okay. So okay. In the output circuit, this is an this I am going to open circuit it. Okay. That means that there is no current which will flow in Q1. Okay. Then in the output side, what will happen to R1 and R2? It will be there or it will not be there?
They'll be there.
It will be there. How? In what configuration?
That case,
See,
RD1, RD2 will come.
in series. Okay. Because I am open circuiting here, so this current source will be removed here. So R1 and R2 will be in series. Okay. So this is going to be the circuit now. Right. In the output circuit, it will be R1 plus R2. Here it will be parallel of R1 plus R2. Correct? Is it okay?
Sir, can you explain this again? Output side, how it is coming?
See,
Input side, I got it.
I remove this circuit. What about this current source? This is a current source, right? In small signal. So this will be current source, right? So if there is no voltage applied to the gate, this current source will go off, right?
Correct.
Right? So I will have R1, R2 ground, right?
Yes.
Okay.
So this will become series.
Series. Okay. Okay.
Okay. So
Yeah.
now this is an transistor. Now what will be the gain of the first stage? Simple equation. If I have RD and RS, what will be the gain? RD by RS, right?
GM into RD by RS.
No. Simple RD and RS. The most simplified is RD by RS, right?
Yeah, RD by RS. Yeah.
Yes.
Correct. So this is the gain, first stage gain. RS, no, this is R1 R2 divided by R1 plus R2, right? This, since in parallel I have written it like this. So R1 R2 will be in the denominator, R1 this will go in the top, correct? Is it okay? First stage gain?
Yes.
Second stage gain, what will be the second stage gain? GM into RD parallel to this thing.
Yes.
Correct? So that is the second stage gain, right? Total gain will be product of these two. Correct?
Yeah.
Yes.
Okay. Total again is product of these two. Okay. Beta we already said it is R1 divided by.
Sir, G2 can you explain? G2
is GMRD.
GMRD.
RL. So GMRL. RL is RD parallel to R1 plus R2.
Okay.
Correct? Okay. Beta is an R1. So I write beta A0. I'll get this particular term. 1 plus beta A0. So I'll get this particular term. Is it okay?
Yes, sir.
Yes. Then forward gain will be A0 divided by 1 plus beta A0. A0 is this. 1 plus A0 is this. Right? So I can write this. So if you consider this RD square as a bigger term, so it will come approximately like this. R1 plus R2 by R1, which is 1 by beta. So the gain is stabilized, if you see here. Is it okay? How to go about doing these kind of problems? Anybody has got it? Okay. Okay. Now input resistance, okay, obviously will be infinite, okay, because this is circuit. Output, output, you don't have to look at this circuit. We'll have to look at this circuit. Output resistance here without feedback, what is it? Can you see? Can you say what is the output resistance?
RD parallel to R1.
Yeah, RD parallel to R1 plus R2, right?
R2.
R0 we are neglecting, okay, obviously. So, and then this is a voltage feedback. So, final resistance, you will have to multiply by this factor or divide by this factor.
Voltage so divided by that factor.
Yeah, since it is voltage, it is divided. Okay, so this is okay. Now this problem is from Millman Halkias. This is probably from your own textbook or Cedra Smith. Many books are there. Okay, so you will get. Okay, okay. This is another circuit out here. Okay, now we are connecting RL out here, and we are putting an R out here, right? So now what kind of feedback is this?
Current.
Yeah.
Negative feedback.
Yeah, negative is there, but are we sampling a voltage and giving here, or we are giving a voltage which is proportional to the current?
So giving a voltage.
We are sampling voltage.
We are not sampling voltage. See, this is the voltage is here, not here. Output voltage is at here. Correct?
So your feedback depends on the current which comes to the R, right?
Correct.
Correct. Yes.
Right? Now, depending on what is the load connected here, the current which is flowing here, a voltage will be developed here. So now it is current and voltage out here, right? Now, if I have to draw a circuit, since it is current, I put current is equal to 0. Correct? Okay. So if I put current is equal to 0, will this R will remain in the input circuit? Tell me.
Will be open circuit. Open circuit will be.
No. This R. This will be there, right? I am putting. Yes. Yeah. So this R will not be there. It will be there, still there, in the input circuit. Okay. Because I am doing an open circuit out here, right? Okay. Now from the output point of view, this voltage source I am removing it here. So obviously, but still this resistance will be there in this full path. Okay. So this R is going to come here also, right? So now this is the equivalence. From here to here, you have to you get an equivalent circuit out here, right? So now if you see here, now you have a circuit. You make an gain equation, right? So normal it is VGS, and there is one R also available here. So output resistance, if you see here, you calculate what is beta in this case.
Beta is almost near to 1.
No, what is beta? What is
Voltage
The
across
same
R.
current
So could you
will
explain the
flow.
output circuit once?
I0? Yeah. Let me just cover this beta aspect, and then beta is equal to V feedback divided by I0. Correct? V feedback is this, right? So beta is R in this case, isn't it?
Yes.
Beta is R?
Correct.
Yes. Okay. So beta will be R. Okay. Okay. Now regarding the output circuit, since we are giving a voltage, we are going to open this circuit out here, right? Now if I go from the drain side out here, okay, I have an RL out here, and if I have to come to the source out here, right? So I have a resistance here from here to here, right? So that resistance will be there here also. Is it okay? So this is the output circuit, this is the input circuit. So this will remain in both these places, right? Now beta is nothing but R, this resistance.
So
Right.
which point is ground here, like in output circuit? This the midpoint of RL and RL, that should be ground, no? Which
for the output circuit, actually if you try to put a ground that might mislead you. We make a loop starting from plus and minus where it was, right? This need not be ground in the output circuit. We just have to complete the loop between the drain and the source of the transistor. Okay. And keep the polarities same. Okay, across which the VOL will be. Here it is a drain. This is positive, and this is negative. Like the voltage is measured like this, right? So we keep that in that case. Or if you put this VDD as ground also, still it will be okay. If you assume it as a from drain, okay, to the transistor, and then VDD and ground. From the source, RL and ground. So they get connected here. Ground.
that's what. This will be the ground point.
Yeah.
That's what I was asking. Okay.
Okay. So once this circuit is there, then this is a pretty simple analysis, right? How to write an equation for them is this V0, right? This current Vs, this entire voltage will be available here. This R is not going to make any difference, right? Because there is no current flowing here. So this will be Gm into this voltage. Output will be okay. This Gm into RL. So you write that in equation, and then you find out beta is R in this case. So into Gm. So we. Is it okay? Is it understood? This R is not going to make any difference either in the input side or in the output. In the input side, okay, right? This voltage will be applied across source, right? No, it is going to make this. There is an R available here, correct? Okay. So you need to write this equation, right? Vs minus
VGS.
yeah, VGS Okay,
So there is no current factor. BES is equal to BGS. Sir.
correct, correct. I think that's how it has been done. Okay, so you need to find out the normal gain, okay, and then beta, and then just in this case, since it is taken in series, okay, so the output resistance will be, you got to multiply it in this particular case, right? It is series, like
So
current.
what is the small RD?
Small RD is R0.
R not equal.
R naught. This is R naught only of the transistor. Okay, this is from Millman-Halkias. They write as RD. That is why in our textbook it is written as R0. Is it okay?
For beta, why it is negative R?
Because here we are saying this is going to the top. This current is going to top. This is the positive terminal. So this voltage will be developed like this, right? And this is going to oppose this voltage. So that is why this negative is given here. Okay. So this is one example. We'll take one more example out here. Here we are feeding it in an current out here. Okay, output voltage is being sampled here. Okay, where is the this is the load resistance. So now what is this? What kind of an feedback is it? Can anybody say? This is the load resistance. RF and RM is put here.
Voltage?
Like voltage, sir.
Voltage?
Voltage is divided here.
No, it is actually, if you see here, this is the output current, right?
Current.
Depending on the ratio of these two resistances, one current will flow here as feedback. Correct? This is one current which is going into this. This is another current which will go from here. A fraction of IO will go here. Okay. So beta will be given by this equation. RM divided by RF. So if you use large RM, more feedback current will go. You use a small RM, then less current will flow here. Is this okay? Beta equation. Like you have potential divider, it is current divider. Okay. So this is an current divider out here. I have I out here, right? And now if I have to make an without feedback, right? I remove this connection. If I remove this connection, right? So I will have RF and RM coming here in the input side. Is it okay? If I remove this connection, right, I am going to put I0 to see the input side without feedback. If I have to see I without feedback, I remove this connection. So in the input side, I will have this current RF and RM. Is it okay? In series. RF and RM will come in series. Right? Okay. Now if you see here, some approximation has been done in this textbook. Here if you see the impedance seeing here, it will be 1 by GM, right? And here if you see the impedance, it is RF plus RM. So you are assuming that, okay, this is much higher. So this entire I is going here, okay? So this voltage out here will be, okay, GM1, okay, same I into RD. This is the voltage. So if that is the voltage, then this current will be GM2 into IRD. So GM2 into RD, right? This is the voltage which is available here. From here, so the current will be GM2 into RD. This current, current gain. Is it okay or is it getting confusing? See, I is IS, okay, because we are assuming that no current is flowing between RF and RM. The entire current is going up because the impedance as seen here will be 1 by GM. So this voltage will be ID into RD, right? This voltage, and this current will be GM into RD. For in this particular case, it will be GM into this resistance, right? Okay. So it is here I have, okay, this voltage is ID into RD, okay, then GM2 into, right, this current I0 will be GM2 into IRD. So that is what it is written here, GM2 into RD, this voltage gain. Is it clear? It's confusing and I don't see any response, so let me clear all the erasing. Okay, I am trying to remove the feedback. If I remove the feedback, okay, I'll cut this connection, right? No current is flowing here. So this will be RF into RM in series, it will come in series, but I am assuming that most of the current is going to flow like this, right? Because the impedance as seen into the source of these transistors will be GM. This is the current amplifier, current into current, okay? So what is the voltage available here? GM2, current available, the voltage available here will be, okay, II into RD. This voltage is, right, II into RD. So what will be this current? GM2 into G. So what will be the current gain? If I just bring this I bottom, it will be GM2 RD. So this is the open loop current gain. Is this equation clear to all of you? Simple, right?
Yes, sir.
Okay. Now what is beta? Beta is I feedback by IO. So IO is coming here. So what is the current which is going here? Okay. Now for that, I am going to put a here I am going to put a ground and see what current will go into which branch. Okay. So for that, now to determine the feedback circuit, I have for a current source I'll put it into ground. For a voltage source, I will leave it into open circuit. Now this is, I have to find out what current will flow here. Okay, if there is no voltage source here. So for that case, it is RL. So now it is an again current divider topology, right? So I write RM, RF by RM. Okay, that is beta. Now this is A, this is beta. Now I can write an AF is equal to 1 plus beta into this. Okay, is this equation clear to all of you now? Is it okay? Okay.
Sir, yeah. Can you explain again?
So in gain cancellation, if we if we take into the effect of this, so in gain calculation, if we take into effect of this IF, like the current which is flowing to RF and RM, then won't it be opposing, like conflicting?
No. See, first I am removing the feedback. Okay, if I remove the feedback, I have to at the output, I am feedback is current, so I make it an open circuit here. So this is IS. Okay, so I am assuming this IS is going to flow, total IS is going to flow here because these resistances are much higher. Okay, here I will take that also into consideration. Time being, just assuming that these are much higher, so this entire current will flow up here. Okay, so this voltage will be II into RD. This is GM into RD, this current, output current, right? So GM into, so this GM into this voltage out here, and this voltage is RD into II. So I get a current gain as GM2 into RD. Is these two equations clear to all of you?
Yes.
Yes, yes.
Okay. Now, is beta clear to all of you?
For beta, you have calculated by removing this RL.
Yes, this is the current which is going to come. Load current. Right? A portion of the load current I am giving it to the input side, and
okay,
I am not giving the full load current here. just a portion of that.
Okay. So, sir, beta actually depends on what we are sampling from output and what we are giving to the input.
Correct.
Okay.
Right. So, is beta clear to all of you?
Yes.
Okay. Okay. Now, after A beta, then I just write this equation, right? This is A divided by 1 plus AB. Then this one. Okay. Is it okay till here? Okay. Now,
Yes,
if I have to take loading also into consideration, okay, then this II, initially I said the entire IS will go there, okay, but the entire IS may not go there if I consider RM, because if I am considering the input, this is not, RF and RM are in series. So in that case, II, which is going here, will be RF plus RM, okay, divided by RF plus RM and 1 by GM. So this resistance is 1 by GM. So again, this II out of this, right, again it is a current divider, right? Is this equation clear to all of you? Current divider, like we did this, right? This is the current divider equation, 1 by GM. Okay. So, so this this entire thing into this IS will not be there. You have to multiply this again here if you want to be more precise. Okay. But this was given in your textbook. Okay. This I have inserted. That is in case you want to be more precise. Otherwise, this is good enough. Okay. So let me take one more example out here. Okay. Here, can you say what kind of sampling is here? Output is here. Okay.
Current.
What are we sampling?
Current.
Current.
And what are we giving here? Voltage, correct?
Yes.
We are sampling voltage and giving current, right? So in the input circuit, what will happen? Input side, since it is a current, I will remove this, right? So 100 ohm, this all thing, this will go series into this, this will become parallel out here, right? Correct?
Yes.
Yes.
In the output side, again, this current source will not be there. So these two will get in series in parallel to this, correct?
Yes.
Yes. So that is shown out here, right? How to draw this circuit. So once having done that, then and what about the feedback? Okay, now you can compute the gain, right? It is like RC1 divided by this for this stage. This will be GM into RC2. For this stage, it will be RC by divided by RS, right? RD by RS. Simple formulas we can use for these kind of circuits, right? Here you have RC and you have RE out here. Okay. Why this is written as instead of drain and source out, because this was actually an BJT circuit which I put MOSFETs out here. Okay, so this is a drain divided by R source. Here it will be just an GM into, because it is the GM into RC2. Here again it will be RC2. So computation of the gain will be straightforward, right? Forward gain is simple, right? Isn't it?
Yes.
Yes. Feedback is slightly, you will have to think, right? What is the feedback? What this current divided by this voltage, right? This is current, and you have to find out the relation between this current and this voltage. This is the feedback voltage. This is the current, right? You have to find out the relation for the feedback. So now what is the current going here? It will be I0 into, right, RE divided by RE1 plus RF. That will be the current which will be flowing here, right? and what will be the voltage? That current into RE1. So you have to find out the relation between I0 and RF from this circuit to find beta. Okay, so that has been done here. Okay, so you can have a look at this. Okay, so I think with that.
Sir, one doubt.
Yeah.
Sir, can you go 2 slide back? So was this one? So, sir, here at output side, how you have computed this resistance circuit, like RF and RE1 will be in series?
So this will go, right? This is a current source. This is we are going to keep it this open. So this will become open. So I'll have RE will be there. This will be in a series, isn't it?
So whenever we are doing for output side, we are making the voltage source as open circuit.
Yes, if it is a current source, we make a short circuit. If it's a voltage source, then we'll open it.
Okay.
It's the other way around in the output. If it is a current, we make it open. If it is voltage, we make it short. In the input side, we do exactly the opposite thing.
So, sir, here this below this transistor, why you are removing this connection? Like above?
Because this current source, okay, is no more there. That's why.
Okay.
Okay, this current. Okay. So that's why I'm doing.
Yeah.
Okay. So this is a normal CS amplifier. This is a CS amplifier with an feedback. Can you see that?
I think R5.
Yeah. So there is a voltage feedback which is given out here. So obviously, if I do an AC analysis, I do this is the signal out here. This is the signal out here, right? So if you see here, this is the green one on top. This is the blue. So obviously, the gain is reduced and the bandwidth has increased. Okay. Now, if I decrease the value, it will be a stronger feedback or a weaker feedback now. If I put
stronger
5
feedback.
Yeah, stronger feedback. So the gain will go further low. Okay, because I am sampling the voltage out here, right? And more current will flow here if I reduce this voltage out here. So if I do this, see, if you see here now, the voltage has dropped further and bandwidth has increased. So if I further reduce it to 2K, okay, if I run, right, now the gain has further come down, whereas bandwidth keeps increasing. Okay, so the gain bandwidth product remains same. Okay, so by giving feedback. Okay, I think we have reached the time limit. I hope this is okay. So this chapter appears to be a bit complicated, but there are a lot of examples you will find in various textbooks. Okay, any electronic device circuits textbooks of BTech level. So I will suggest you do some practice problems, and in case you are getting stuck with those practice problems, then feel free to get in touch with me.